Hey everyone, and welcome back to Organic Chemistry on YouTube. Today we're going to talk about rearrangements that are possible during E1 reactions. We're going to use examples that invoke alkyl halides. Here's what you need to know about the rearrangements. First of all, the vast majority of the examples that you'll see in introductory organic chemistry involve the transfer of a hydride ion. So this is just a hydrogen with one extra electron. So one proton and two electrons. And the process will involve the transfer of this hydride ion from one carbon to an adjacent carbon. This occurs when there's a more stable carbocation that's possible after rearranging, and it's sometimes a concerted process. Let's start first with this example of a secondary alkyl chloride. We've got this starting material with ethanol and heat as the reaction conditions, and you form a tri-substituted alkene, the Zaitsev product. And the product is a tri-substituted alkene, which is the major product. I'm omitting the other minor products for the moment to highlight the role of the hydride transfer in this reaction. So in this reaction, like the two electrons that are in the carbon-chlorine bond will move onto chlorine, since chlorine is a very good leaving group. And the resulting carbocation intermediate looks like this. And you'll notice that this is a secondary carbocation. When I'm looking at E1 reactions and SN1 reactions, I always look to see if there's a possible shift of this cation to another more substituted position. So when I look to the left, I notice that if I were to move the cation here to the left, it would be a secondary carbocation, which is the same energy as it currently is. So there's not really a driving force for the reaction to go. But if I look to the right, there's the possibility of moving the cation over and having a tertiary carbocation, which is more stable than a secondary carbocation. So when you have that kind of situation, then it's possible for the hydride to shift and to do a carbocation, for the carbocation to shift to a tertiary position. So here the hydride moves over, okay, and this is the two electrons from the carbon-hydrogen bond move over to the current cation position. You now have a tertiary carbocation, okay? Remembering that this is an elimination reaction and you have to get to an alkene at the end of it, you realize that you need to deprotonate this reaction. Now, the only hydrogens that you can deprotonate to actually get to the major product, which is the mechanism that we need to draw, are these. Either of these are identical. So ethanol, our base, can be used to make a bond with that hydrogen and push the two electrons from the carbon-hydrogen bond onto the hydrocarbon framework and make the alkene that's ultimately formed. Okay, so that's how you arrive at this, this product. Now, there are sometimes concerted reactions. Those involve almost always the generation of primary carbocations. Okay, so if we started with this substrate, the first step of an E1 reaction is always that the leaving group leaves. Now, if this one tries to leave, right, you'll end up with a primary carbocation, which, as we've talked about before, is extremely high in energy and is not correct to draw. But there is a mechanism by which this chlorine could leave as a carbocation is being formed. So in this instance, the chlorine could leave as the carbon-hydrogen bond, the hydride, shifts to this carbon. And as it does, you'll end up with a secondary carbocation, right? The chlorine has left, and then you can use whatever base you were using, say ethanol again, to deprotonate one of the hydrogens and then form the propene molecule. Okay, so from here, things you might want to ask in office hour. One, can you observe a hydride shift for an energetically unfavored carbocation? For example, going from a secondary to a primary carbocation, is that possible? And are there any reaction conditions that would promote that? Two, are there any stereochemical implications for hydride shifts? Are there any requirements that the hydride, have some kind of orientation relative to the cation to allow this kind of hydride shift? Okay, that's been Organic Chemistry in 5 minutes or less. Thanks very much for tuning in.